Hi, it's Mr. V, and today is the next to last day of summer school for Honors Algebra 2. We're going to be talking about conics. It's a relatively long lecture. I'm going to try to make it interesting and as short as I can. We'll start off by talking about completing the square. This is something that many people do in Algebra 1. It's something that is useful when we go to talk about conics, because if you have perfect squares, like x plus r squared or x minus r squared, then it'll be some of the problems will be easier to see or easier to solve. And sometimes you're given a problem where it's not a complete square. Doesn't look like this. So to complete the square, you'll want to have an expression x squared plus 2r times x. And what you want to do is to find r, which is half of the 2r part of it, and then square it. So it takes on this form right here to look like a perfect square, and then you can make the square binomial. If it's got a plus sign, it'd be like this. If it's got a minus sign, it'd be like this. So let's look at a couple of examples. Remembering these are our perfect squares that we're trying to get this to look like. This is not a perfect square. We need to find out what value of c will make this a perfect square. And to do that, the first thing I'm going to do is take half of 12. That's going to give me my r value. And then we square it to get 36. That'll give me my r squared. So if I add this to both sides of, or if there's an equation, I would add it to both sides. But if I were to add it where c is, that'll give me 36, and that's a perfect square. X plus 6 squared. The kind of problem you might see is something like this. Solve this by completing the square. And I think we have a few problems like that in our practice. This part of the lecture is only about the notes, and in a moment I'll give a separate lecture where we actually work through a few problems. So here, you'll notice this is not a perfect square. So the first thing I'm going to do is get the 10 on the other side of the equation by adding 10 to both sides. Now I've got this 2r value, and I need to know what r is. When I take r and I divide it by 2, I get 64. Well, you have to do one thing to one side of the equation is to the other, so I'll add 64 to this side. The equation gets 74. And now we have a perfect square on the left side of the equation when we factor it, which makes it useful for solving. To solve this, we'll take the square root of both sides. When you take the square root, remember you'll have a plus or minus sign for the square root. And so this gives us the solution is a negative x plus or minus the square root of 74. We're talking about conics. They call this a conic section because if you have an inverted cone and you were to take slices of it, it would be one of four shapes. It would be a parabola. Might not have known that's a slice of a cone. If you take a line parallel to one of the bases here, this would be a circle, and if it's a little bit off, it would be an ellipse. We'd also one that's parallel to the axis and perpendicular to the horizontal axis, and this would give us what's called a hyperbola. Talking about quadratics, you're familiar with the form ax squared plus bx plus c. When graphed, it gives you a parabola. What you may not be familiar with is the definition of the set of points that are equal distance from a given point, called the focus, and a line. So this distance, P1 to F and P1 to D1, is the same distance. This distance here from here is the same distance. And a parabola could be defined like that. If we had time and we were using GeoGebra, we would actually build something like this to show you what it looks like. And so to help you understand parabolas, I've given you this graphic organizer. We've talked about standard form, vertex form where h and k is the vertex, root form where r1 and r2 is the root form. This one has a leading coefficient of 1. And the focus and the directress, this is new. And there's this thing called the latus rectum. It's a segment with endpoints that are on this is the latus rectum. So if you take 2 points that are horizontal to this would be the latus rectum is this distance. Now, 1 over. So you may not be used to this. You're used to seeing A here and 1 over 4p, where p is the value we'll be looking at shortly. When you leave Algebra 2, you should be able, and much of this is from Algebra 1 as well, but you should be able to locate of a parabola the vertex, the axis of symmetry, the y-intercept, the roots on the x-axis, x-intercepts as well, if there are any. If it's imaginary, you won't have any. You should be able to tell if it opens up or down, if it's compressed or narrow or stretched. And from the discriminant, you're going to tell if there's 1 real root, 2 real roots, or 0 real roots. And today we're also going to do finding the directrix and the focus. So this blue table shows some really good information, really important information. Also, there's some good practice that if you want to get good at this, you might want to try some of these. Just do the practice here. Though this is not a function, but it is yet a parabola. And it could open horizontally, and this would be the equation that you would use where it opens horizontally. And you'll notice the function, the focus. The focus is your horizontal value, the value of the vertex, hk, plus the p, when it's this direction. Here's the vertex hk, and k plus the p when it's opening vertically. Everything we'll do will come from these equations. And here's a summary table. Circles. Circle is of the form x squared plus y squared is equal to the radius squared. And actually it's like this, where h and k is the center. When you have an ellipse, which looks like a stretched circle, every ellipse has 2 axes of symmetry. It has one that's horizontal and one that's vertical. The longer one is called the major axis. The shorter one is the minor axis. The endpoints of the major axis are vertices. The endpoints of the minor axis are co-vertices. And the center is where the 2 axes intersect. So here are the formulas. This is what is important. You'll notice that a squared, you usually think of a squared plus b squared as c squared. When you're talking about an ellipse, we're looking at this distance being b, this distance from the center to one of the vertices, the vertices is a, and c is going to be a squared minus b squared is going to give you c squared. So that'd be the way you would find c squared. And if it's a horizontal major axis, this is the form it takes. Vertical major axis, this is the form it takes, where a, let's see here, I believe a, this distance is a, is always going to be the distance. 2a is going to give you the distance of the major axis, whichever way you're going. So if it's x over a squared, it's going to be horizontally relocated. If it's y over a squared, it's going to be vertical. Something to watch for. And here's a summary. Hyperbola is a set of points in a plane such that the absolute value of the difference of the two given points or foci is constant. Well, it's kind of like a parabola, only in a parabola we had it from this point to this point. From this line here to this point here is going to be the constant. Here we have, notice the transverse axis is this distance between the two, the way that they're opening. And the conjugate axis is the one that is perpendicular to this for transverse axis. This is what it looks like in an equation. And when you see this, notice this difference between the x squared over a squared minus the y squared. When we had an ellipse, this was a positive. So now it's going to be a negative. And once again, the a distance is going to be the distance along the transverse axis. The 2a is going to be the distance along the transverse axis. And if it's horizontal, it's going to be x squared over a squared. If it's vertically oriented, it's going to be the y squared over a squared. And in each case, you're going to be looking at formulas. I've prepared a sheet here which summarizes everything. If circles don't open horizontally or vertically, but parabolas can, you can have a ellipse can be horizontally or vertically oriented, and same with the hyperbola. And here are the formulas that you would use, and we'll do some practice problems.